Hello. Welcome. You got it right. Hola, 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 hola. Listo. Finally. Listo. Okay. What are we gonna do today? What are we doing today? What we are doing today? Have some fun. What are we doing today? What we are doing today? Okay. We're going to the. We're going to learn. What are we learning this morning? We're going to learn about regression model. You like regression model? Regression model. I don't even know what is that, bro. I don't know. Let's play it. You just play it.
In this video, we'll look at what the overall process of supervised learning is like. Specifically, you see the first model of this course, a linear regression model. That just means fitting a straight line to your data. Is probably the most widely used learning algorithm in the world today. And as you get familiar with linear regression, many of the concepts you see here will also apply to other machine learning models that you see later in this specialization.
Okay. What?
Let's start with a problem that you can address using linear regression. Say you want to predict the price of a house based on the size of a house. This is the example we seen earlier this week. We're going to use a dataset on house sizes and prices from Portland, a city in the United States. Here we have a graph where the horizontal axis is the size of the house in square feet, and the vertical axis is the price of the house in thousands of dollars. Let's go ahead and plot the data points for various houses in the dataset. Here, each data point, each of these little crosses, is a house with a size and a price that it most recently was sold for. Now, let's say you're a real estate agent in Portland, and you're helping a client sell a house, and she's asking you, how much do you think you can get for this house? This dataset might help you estimate the price she could get for it. You start by measuring the size of the house, and it turns out that her house is 1,250 square feet. How much do you think this house could sell for? One thing you could do is you can build a linear regression model from this dataset. Your model will fit a straight line to the data, which might look like this.
Let's start all over
And
again.
based
because
on this straight line fit to the
I didn't
data
even put attention.
to other machine learning models that you see,
Okay.
of course,
Linear regression model part 1.
model.
Linear regression model part 1.
In this video, we'll look
Regresión
at
lineal.
what the overall process of supervised learning is like. Specifically, you see the first model of this course, a linear regression model. That just means fitting a straight line to your data. Is probably the most widely used learning algorithm in the world today. And as you get familiar with linear regression, many of the concepts you see here will also apply to other machine learning models that you see later in this specialization.
Linear regression is a model, just a straight
Let's
line.
start with a problem that you can address using linear regression. Say you want to predict the price of a house based on the size of a house. This is the example we seen earlier this week. We're going to use a dataset on house sizes and prices from Portland, a city in the United States. Here we have a graph where the horizontal axis is the size of the house in square feet, and the vertical axis is the price of the house in thousands of dollars. Let's go ahead and plot the data points for various houses in the dataset. Here, each data point, each of these little crosses is a house with a size
and size. Size fit and the price. Okay. And what the y-axis is the price.
Agent in Portland,
We have that.
and you're helping a client sell her house. And she's asking you, how much do you think you can get for this house? This dataset might help you estimate the price she could get for it. You start by measuring the size of the house, and it turns out that her house is 1,250 square feet. How much do you think this house could sell for? One thing you could do is you can build a linear regression model from this data set.
Algorithm.
Your model will fit a straight line to the data, which might look like this. And based on this straight line fit to the data, you can kind of see that if a house is 1,250 square feet, it will intersect the best fit line over here. And if you trace that to the vertical axis on the left, you can see the prices maybe around here, say about $220,000. So this is an example of what's called a supervised learning model. We call this supervised learning because you are first training your model by giving it data that's the right
So we
answers.
first train a model,
Because you
right?
give the model examples of
Don't
houses
look at my
for both
butt.
the size of the house as well as the price that the model should predict for each house. Where here the prices, that is the right answers, are given for every house in the data set. This linear regression model is a particular type of supervised learning model. It's called a regression model because it predicts numbers as the output, like prices in dollars. Any supervised learning model that predicts a number such as 220,000 or 1.5 or negative 33.2 is addressing what's called a regression problem.
The numbers are
So
regression.
linear regression is one example of a regression model, but there are other models for addressing regression problems too. And we'll see some of those later in course 2 of this specialization.
You see it? You
and
can
just
imagine
to
that.
remind you, in contrast with the regression model, the other most common type of supervised learning model is called a classification model.
Classification.
A classification model predicts categories or discrete categories, such as predicting if a picture is of a cat, meow, or a dog, woof. Or if given a medical record, it has to predict if a patient has a particular disease. You see more about classification models later in this course as well. So as a reminder about the difference between classification and regression, in classification,
regression model predicts numbers. Supervised learning models that has the right answers.
Versus dogs, that's 2 possible outputs. Or maybe you're trying to recognize any of 10 possible medical conditions in a patient. So if there's a discrete, finite set of possible outputs, we call it a classification problem, whereas in regression, there are infinite categories, possible numbers that the model could output. In addition to visualizing this data as a plot here on the left, there's one other way of looking at the data that would be useful, and that's a data table here on the right. The data comprises a set of inputs. This would be the size of the house, which is this column here. It also has outputs. You're trying to predict the price, which is this column here. Notice that the horizontal and vertical axes correspond to these 2 columns, the size and the price. And so if you have, say, 47 rows in this data table, then there are 47 of these little crosses on the plot of the left, each cross corresponding to 1 row of the table. For example, the first row of the table is a house with size 2,104 square feet, so that's around here. And this house sold for $400,000, which is around here. So this first row of the table is plotted as this data point over here. Now, let's look at some notation for describing the data. This is notation that you find useful throughout your journey in machine learning. As you increasingly get familiar with machine learning terminology, this will be terminology that you can use to talk about machine learning concepts with others as well, since a lot of this is quite standard across AI. You'll be seeing this notation multiple times in this specialization, so it's okay if you don't remember everything the first time through. It will naturally become more familiar over time. The data set that you just saw and that is used to train the model is called a training set. Note that your client's house is not in this data set because it's not yet sold, so no one knows what its price is. So to predict the price of your client's house, you first train your model to learn from the training set, and that model can then predict your client's house's price. In machine learning, the standard notation to denote the input here is lowercase x, and we call this the input variable. It's also called a feature or an input feature. For example, for the first house in your training set, x is the size of the house, so x equals 2104. The standard notation to denote the output variable, which you're trying to predict, which is also sometimes called the target variable, is lowercase y. And so here, y is the price of the house, and for the first training example, this is equal to 400. So y equals 400. So the dataset has one row for each house, and in this particular training set, there are 47 rows, with each row representing a different training example. We're going to use lowercase m to refer to the total number of training examples, and so here m is equal to 47. To indicate a single training example, we're going to use the notation parentheses x comma y. So for the first training example, x comma y, this pair of numbers is 2104, comma 400. Now, we have a lot of different training examples. We have 47 of them, in fact. So to refer to a specific training example, this will correspond to a specific row in this table on the left. I'm going to use the notation x superscript in parentheses I, comma, y superscript in parentheses I. The superscript tells us that this is the ith training example, such as the first, second, or third up to the 47th training example.
Got a table that is called
refers to a specific row.
Each of them has an input, which is the x-axis, and the target variable, which is the y-axis.
The first example,
and you can refer to each of those targets
and so
or
x
inputs
1
with the
is equal to 2104,
y, right?
and y superscript 1 is equal to 400.
Refers to
and let's add the superscript 1
row of the
here
data
as well.
of the data table.
Just a note, this
Like
superscript I in parentheses is not exponentiation. So when I write this is not x squared. This is not x to the power of 2.
It's not x squared.
It just refers to the second training example. So this I is just an index in the training set and refers to row I in the table. In this video, you saw what a training set is like, as well as the standard notation for describing this training set. In the next video, let's look at what it'll take to take this training set that you just saw and feed it to a learning algorithm so that the algorithm can learn from this data. Let's see that in the next video.
You have 3 days. Good. Okay. Let's process that. Okay. So we have machine learning, by definition, is giving the ability to the computer to learn without being explicitly programmed, right? That's what it is. That's what it is, like machine learning. The computer is going to learn. You don't have to program it to do it. They will learn. But there are different kind of learning. So you have unsupervised and supervised learning, right? We're currently using supervised learning on most of the applications. Also, this one gives you, so you have to give it, like to this algorithm, you have to give it an input, an X, and it's going to give you an output, Y, right? So you can make it, you can train it to understand the pricing of the housing market based on the size and and the price of several properties or listings, you will be able to predict numbers based on that using regression model. That's what I understood. So basically, regression model is going to give you numbers, so it's going to predict numbers. Supervised learning is going to give you the right answers to a question. And classification model is going to tell you, okay, this is a dog, this is a cat. It's going to tag things. To wrap this video, we learn about the terminology, which is basically the training set, which is all the data. We have the input and target, which is X and Y. If you want to refer to a specific input, you will have to give it a place, an index of the two. So X2 will be the second item. That's what I got. That's good. What do you understand about it? Give me your thoughts about it in the comments. I think it was pretty straightforward. Let's keep learning. Let's do the second part. In this second part, let's fully understand it. What is a linear regression model? Hopefully, we'll have an example here, and after that, we will do a laboratory for model representation. That's gonna be fun, right? Okay. Let's do it.
Let's look in this video at the process of how supervised learning works. Supervised learning algorithm will input a data set, and then what exactly does it do and what does it output? Let's find out in this video. Recall that a training set in supervised learning includes both the input features, such as the size of the house, and also the output targets, such as the price of the house. The output targets are the right answers that the model will learn from. To train the model, you feed the training set both the input features and the output targets to your learning algorithm. Then your supervised learning algorithm will produce some function. We'll write this function as lowercase f, where f stands for function. Historically, this function used to be called a hypothesis, but I'm just going to call it a function f in this class. And the job of f is to take a new input x and output an estimate or prediction, which I'm going to call y hat. And it's written like the variable y with this little hat symbol on top. In machine learning, the convention is that y hat is the estimate or the prediction for y. The function f is called the model. X is called the input or the input feature, and the output of the model is the prediction y hat. The model's prediction is the estimated value of y. When the symbol is just the letter y, then that refers to the target, which is the actual true value in the training set. In contrast, y hat is an estimate. It may or may not be the actual true value. Well, if you're helping your client to sell their house, well, the true price of the house is unknown until they sell it. So your model F, given the size, outputs a price which is the estimated, that is the prediction of what the true price will be. Now, when we design a learning algorithm, a key question is, how are we going to represent the function f? Or in other words, what is the math formula we're going to use to compute f? For now, let's stick with f being a straight line. Let's look in this video at the process of how supervised learning works. Supervised learning algorithm will input a data set, and then what exactly does it do and what does it output? Let's find out in this video. Recall that a training set in supervised learning includes both the input features, such as the size of the house, and also the output targets, such as the price of the house. The output targets are the right answers that the model will learn from. To train the model, you feed the training set both the input features and the output targets to your learning algorithm. Then your supervised learning algorithm will produce some function. We'll write this function as lowercase f, where f stands for function. Historically, this function used to be called a hypothesis, but I'm just going to call it a function f in this class. And the job of f is to take a new input x and output an estimate or prediction, which I'm going to call y hat. And it's written like the variable y with this little hat symbol on top. In machine learning, the convention is that y hat is the estimate or the prediction for y.
Okay.
The function f is called the model. X is called the input or the input feature, and the output of the model is the prediction y hat. The model's prediction is the estimated value of y. When the symbol is just the letter y, then that refers to the target, which is the actual true value in the training set. In contrast, y hat is an estimate. It may or may not be the actual true value. Well, if you're helping your client to sell their house, well, the true price of the house is unknown until they sell it. So your model f, given the size, outputs a price which is the estimated, that is the prediction of what the true price will be. Now, when we design a learning algorithm, a key question is, how are we going to represent the function f? Or in other words, what is the math formula we're going to use to compute f? For now, let's stick with f being a straight line. So your function can be written as f subscript w comma b of x equals, I'm going to use w times x plus b. I'll define w and b soon, but for now, just know that w and b are numbers, and the values chosen for w and b will determine the prediction y hat based on the input feature x. So this fwb of x means f is a function that takes x as input, and depending on the values of w and b, f will output some value of a prediction y hat. As an alternative to writing this fw comma b of x, I'll sometimes just write f of x without explicitly including w and b in the subscript. It's just a simpler notation, but means exactly the same thing as fwb of x. Let's plot the training set on the graph where the input feature x is on the horizontal axis and the output target y is on the vertical axis. Remember, the algorithm learns from this data and generates a best fit line, like maybe this one here. This straight line is the linear function fwb of x equals w times x plus b. Or more simply, we can drop w and b and just write f of x equals wx plus b. Here's what this function is doing. It's making predictions for the value of y using a straight line function of x. So you may ask, why are we choosing a linear function where linear function is just a fancy term for a straight line instead of some nonlinear function like a curve or a parabola? Okay. Well, sometimes you want to fit more complex nonlinear functions as well, like a curve like this. But since this linear function is relatively simple and easy to work with, let's use a line as a foundation that will eventually help you to get to more complex models that are nonlinear. This particular model has a name. It's called linear regression. More specifically, this is linear regression with one variable, where the phrase one variable means that there's a single input variable or feature x.
Linear regression with one variable.
Another name for a linear model with one input variable is univariate linear regression, where uni means one in Latin and where variate means variable. So univariate is just a fancy way of saying one variable. In a later video, you'll also see a variation of regression where you want to make a prediction based not just on the size of a house, but on a bunch of other things that you may
Okay,
know about
not
the
just the
house, such
size.
as the number
Okay,
of
got it.
bedrooms and other
Okay, okay,
features.
okay. So, gotcha, gotcha. So, that's good. The training set. Oof, that was hardcore, bro. That was cool. Okay, I think that means. It was hardcore. Okay, tiene que estar. Ok, estuviera bien, preguntaras. A ver, para meternos a grupos o a algo. Estuviera interesante. Vamos a preguntar. Ujú. Pero creo que sí entendí. En la terminología, entonces, específicamente la terminología. Specifically in the training set, sorry, I was speaking in Spanish. I don't know if we should be doing this in Spanish or English. But I think that in English is better. I don't know. Okay, so we have the training set, which is what we give to the model to learn from. You give them input features and target variables, right? X and Y. You can refer to them with an index. Okay? So, based on the training set, you have the learning algorithm, but you need a function in order to that to function, right? Okay. So, how do you express that? How do you represent this function? This is the one. Is FWB x equals to WX plus B, right? Which is the same as Fx equals to WX plus B, which the outcome depends on the values that you are passing in. So currently we have a linear regression univariate, something like that. Univariable or univariate, something like that. So we have the linear regression, which that means this is only get one variable, which is the size. And based on that one variable, you can predict that number using a regression model. Yeah, that's it. That's it. That's the entire thing. So what happens when we want to add more variables to, to this uh, to this program? Not only based on the size. Maybe we want to know the number of rooms. I don't know, whatever other values. The location. Yep. So that's it. That's what I got from now. Mm-hmm. Let's keep going. I think that what is next? Oh, okay. This is a question. Okay, for linear regression, the model is represented by W by F W B X equals to W B plus B. Oh man, oh X. Okay, it's X plus B. Which of the following is the output or target variable? The output or target variable is the X, the Y. The Y is the target variable. Remember that. You need to remember that. The first one that is this Y hat is a estimation of Y. So it's not the target value. And the X right here is the feature input, right? Yes, I think. And the M, what is the M? The model? That doesn't even make sense. I don't even know what is the M. Maybe model, but it's Y. So you do Y, oh man, retry. Y, submit, correct. Perfect. Woo!
And by the way, when you're done with this video, there is another optional lab. You don't need to write any code. Just review it, run the code, and see what it
Let's
does.
do it.
That will show you how to define in Python a straight line
Oh,
function.
nice.
And
We're going
the
to learn
lab
how
will
to
let
define
you
a function,
choose
bro.
the values of W and B to try to fit the training data. You don't have to do the lab.
I
if you
will
don't
do
want
it,
to,
bro.
But I hope you play of it when you're done.
If you don't do the
watching this
labs,
video.
you are wrong. Everything
So,
is wrong.
That's linear
Do it.
regression. In order for you to
Just
make this
do
work,
it.
one of the most important things you have
Make
to
your
do is
things come
construct
true.
a cost function. The idea of a cost function is one of the most universal and important ideas in machine
It
learning.
was very
and it's
fun.
used in both linear regression and in training many of
Machine
the most
learning.
advanced AI models in the world. So let's go on to the next video and take a look at how you can construct a cost
Let's
function.
have, we're going to look at video. Okay, it's a model representation laboratory, which is the funniest thing. Okay, it's not fun. Yes, it is. Okay, let's do a quick break. Be right back. Regresamos. La actitud es todo. La actitud en el estudio. ¿Quién está viéndome ahí, El que me esté viendo, que mande un mensajito y diga, hello, hello. Okay, let's begin with the optional lab. Okay, but do this. Okay. What I'm going to do here, we're going to do this lab in the other machine. Let's try to see how this works. Oh man. Geekoteka bot. Okay. We're in. Skip. Open lab. We have two labs here. Let's put the second video down here and let's check the laboratory. So, Jupyter C1W1 Lab O2 model representation. Model representations. Okay, so this image here we already did it, which is basically what we have at the back. But let's review it. This is how we represent the function in order to output the result of the linear regression model, right? So how do we represent the linear regression model in a function, in a mathematical way? So it's this one right here, fwb x equals to wx plus p, which is the same as fx, right? So the output will change based of factors, like will be, in this case, it's just one variable. That means that it changes based on the size of the house. So this right here at the right is called the data table training set, which is what we feed to the learning algorithm, which will be in that the learning algorithm is the linear regression using one variable, right? That is also called univariate, right? Which means one variable. So you give the function a feature, and it will give you an estimate y, which is y hat. Okay. So the the goals of this lab is to learn to implement the model FWB for linear regression with one variable. Okay. Okay. Notation. Here's a summary of some of the notation you will encounter. General. notation AA, regression X, Y, X, Y, M, W, B, F, F, W, B, X, the result of the model equation. Okay. Okay, this is just how we represent. These are the notations of of the or the terminology, right? So A is scalar non-bold. Okay, vector because it's bold is going to be vector. Oh, nice, nice. Okay. Increase hard. Okay, I don't know what I did. Shift. Okay, okay. X is the training example feature values, right? So this is the size. On the data table, you have X. You also have Y, which is the training target, which is the prices. X train in Y train, if I program Python. Okay. And X index, Y index, the training example. How do you pronounce this? It's like the first. Mm-hmm. Okay. M, the number of training examples. Okay, there you go. Okay, so this is M. I thought it was, I don't know what was I thought before, the model, but it's number of training examples. So you have in the data table, you have 1,000 records. So those M will be 1,000, right? Okay, it makes sense. Hmm. So you have the W, which is the weight, and the bias. I don't know what's the bias and the y and the weight. So the result of the model evaluation at X index parameterized by WB, mhm, FWB X index equals to WX index plus B. Okay, let's just absorb that for now. We know that there is a function. We know that this will evaluate a feature value of a training example and will give an output target, which is the Y. Oh. And this output will change depending of the parameters that we have of WB. Okay, got it, got it. WB is weight and bias. Okay, so on the function that we previously saw is F weight bias, okay, X, the index equals to weight, the X, which is the X train, plus the bias. I don't still know what's the bias. I mean, I know what is bias. So you have a certain, how do you call that? Mm, bias, like technical bias. When you have like this kind of assumptions. I don't know what's the proper word. Okay. So after seeing this notation, we are kind of familiar with all of it. FWB. Okay, so tools. In this lab, you will make use of NumPy, cool, NumPy and Matplotlib. So NumPy is a way of handling n-dimensional array. So it can be an array, a multi-dimensional array, right? So it's fast and versatile. The NumPy vectorization, indexing, and broadcasting concepts are the de facto standards of array computing today. So it's computing arrays, the scientific computing way, correct? Okay. You have numerical computing tools, offers comprehensive mathematical functions, random numbers, generators, linear algebra routines, and Fourier transforms and more. Okay, so basically a math library. And we will put it together with a Matplotlib. Matplotlib, which is a tool for visualization, right? So it's a comprehensive library for creating static, animated, and interactive visualizations in Python. Okay, so plot lib makes easy things easy and hard things possible. We can do interactive figures. To get interactive visualization, you must run the notebook cells in order. You can hit play triangle above. Okay. Play it. Time series example. Now what? Load data. Open small. And then here we plot time. Okay, let's plot time. Observation dinosaur color, temperature. Wow. Invalid. Okay. Well, we can get an idea of what you get. You get a nice visualization using like all the data. This is nice. Image data, global land surface temperature. Okay. Load data. There you go. So you load the data from NumPy, I guess, then from text, you get the CSV, you put a delimiter on it, then you are making a query where the data is less than 1000. I don't know what it's doing this, that, I don't know what it's doing here. Then it's going to do some latitude, longitude arrangement here, date, and the source. Okay. Then you plot the data you are using. You're going to use big, ax, plot, subplots, constraint layout, fixed size. Okay. Hmm. Nice. Uh, that's how I learn. I just try to break things. Okay. What else should we have here? For example, if I do p-color mesh. Oh, p-color mesh. Mhm. Where is the CMap option? CMap. CMap. It can be color map. Where are the colors? Viridis. Let's try this. Oh, you see, now we have a different color. We learn about this p-color mesh, right? P-color mesh, which is, what is it? P-color mesh. Creates a pseudo color plot with a non-regular rectangular grid. Okay, so we need to pass colors. I didn't find them here, so I just went crazy a little bit and just click a little bit on the code. And I don't know how I got here, but I saw this guy. So I suppose this is The colors, I don't know. If you know another one, just let me know. Okay, cool. Let's keep going. Okay, this is why labs are cool. So import numpy as np. It's easy. You have numpy here. Now we know. And we also have the matplot, the plot, pyplot from matplot library. Okay, and you are using these styles. I don't know where we're getting this from, but that's fine. So, as is as in the lecture, you will use the motivating example of housing price prediction. This lab will use a simple data set with only two data points. Two data points. Two data points. Mhm. But that means that it's going to be one variable only, so it doesn't mean that it's, so yeah, it's only variate. A house with 1,000 square feet sold for $300,000, and a house with 2,000 square feet sold by $500,000. These 2 points will constitute our data or training set. Remember the training set, right? We have the data table, which is the training set that we will feed the model with. You gotta eat, man. You gotta feed that model with some numbers. Eat them, and until you throw, and give me a Y. Give me a Y, man. you know. So these 2 points will constitute our data training set. In this lab, the units of size are 1,000 square feet. I hate the square feet. Come on, guys. Go and use meters. And the unit price are 1,000 square feet. No, $1,000. Okay, the price units. Okay. So we have two data points. Uh, the size, we have 1,000 square feet, 2,000 square feet, and the price of dollars respectively will be $300,000 and $500,000. So you would like to fit in a linear regression model. Basically, we want to put a straight line, okay, through the graph shown above as the blue straight line. Mhm. Through these 2 points, so you can then predict the price for the houses. Okay, say a house with one 1,200. I hate these numbers. 1,200 square feet. Okay. Okay. So we need to predict what's the price range for that based on these two data points. So in order to do that, we need to run the following code cell to create our own X train and Y train variables. Okay, the data is stored in one-dimensional NumPy array. It's just one dimension. It's not multidimensional. One dimension is just an array, a simple array like this. Okay, an array, two indexes separated by a comma. That's it. That's one-dimensional array. And we want to get from these points, we want to get the x and the y. So remember, the x is the input and the y is what the output, right? So it will be the target variable. The y is the target variable and the x is the input feature. Okay. Okay, so if we want to get the x train, we will grab whatever we have on the x column, right? Which are 1 and 2. So we want to get 1.0 and 2.0 into the NP array. Okay, we want to treat it. We want to create a code cell for that. A code cell. I don't know what's a code cell. We will know. Okay, and for the X train, we do the same. We are going to use the NP array, and we are going to abstract from our data. We are going to grab the Y, which is the target variable. Okay, so we have 300.0, 500.0, and then we are going to print them. That we are passing in the f, we are passing a variable. Remember that we can pass variables to Python, right? So what we're going to print is going to get, I don't know, two values. What do you think? I guess we're going to get like an average or something. I don't know, man. Oh no, there you go. Okay, so you get this. Oh, okay, so you get this thing. This is not an array. Check this out. This is like an array, right? But it's an array, yes. But it doesn't have any comma. It's not being separated. They are just the values, and it doesn't have any reminder here, right? How do you call that? Decimal. So, okay. So at the end, instead of having 1.0, comma 2.0, you get this array-like thing, which has the first value, which will be the x y1 and the x2, and then you get the y1 and the y2. Okay. This course will This course will frequently utilize the Python f string output formatted described here when printing because it's just passing in a variable. I'm not going to go there. The content between the curly braces is evaluated and then producing the output. Okay, you evaluate it and then you produce that. So, what else do we have here? Okay. So, the number of training examples, m, remember, is a number of training examples. In this case, will be two, right? Because we have two data points. So you will use m to denotate the number of training examples. Okay. Mm-hmm. Training examples is not data points. Yeah, it is. Everyone is a training example. Mm-hmm. Thank you for following. Thank you for following, man. Oh, there are no alerts. I just heard that. W, what's your name? That was pretty happy, bro. If you're following W1JZW1 underscore Q9, don't hack me, please. So we are learning machine. We are learning deep learning, machine learning. I'm a noob, so we're just making sense of the foundations, like the concepts, the algorithms behind it, the functions that represent those algorithms, and right now we're just trying to make sense of every concept and how everything fits together. So yeah, currently we are checking in a Jupyter notebook, which we are working on the model representation for the linear regression model. So okay, so you will use M to denotate the number of training examples. NumPy arrays have a dot shape parameter, which is this thing, right? Dot shape parameter? I don't know. Yeah. Xtrain dot shape. Yeah. Xtrain dot shape. Okay, a parameter you can access. I will be able to access this x underscore train dot shape will return a Python tuple with an entry of for each dimension. Okay, with an entry of each dimension. For example, xtrain.shape index 0 is the length of the array and number of examples as shown below. Okay, so m is the number of training examples. So we have fxtrain shape and xtrain shape. It's going to print this entire parameter from shape, and then it's going to get the number of training examples accessing this index 0. This index 0 will have the length of the array and number of examples. So we should get the array of the length, the array is 2, right? Yeah. So you get x train dot shape, it will give you this entire thing. Give you this. It's a Python tuple. So yeah, Python tuple is not. I don't know how to work with Python tuples. So let's work. Mhm. Okay. Mhm. It's just uh, is an array like is separated by commas. Uh, you can store multiple items in a single variable. Tuple is one of the four built data type. So you have list, set, and dictionaries, okay, in Python. So in this case, it's a tuple, which is a collection which is ordered and unchangeable. This is the key, I guess. When you don't want to change anything from that, you it's not changeable, right? So it will give you a tuple that you can access. You cannot change. I mean, it doesn't make sense on changing, right, that shape or the length of the array. So you will get a tuple on that, so you can access. So this is a tuple, and how do you access those tuples? Well, you just pass in an index, right? So this index two, the index zero is the number here. So if I say, for example, give me the index, oh, give me this index. Let's see, it's going to be empty or okay, there's nothing there. So if I do X, right? Okay, and what happens if I do Y train? Do we have here, I guess, going to give you two also, right? Mm-hmm. Yeah, because it's going to give you the number of the length is going to give you a tuple with a each. That tuple have each entry for each dimension. For each dimension. Okay. So if you had something multiple dimensional array, it will change. Okay. Okay, so if we do, for example, multidimensional, let's do multidimensional here. Let's just pass in this here and do 3 and 4. Okay. So you have a multi-dimensional array. Now you have the X train. This should change. It will give you a length for each of it. So it will give us a tuple with 2, 2, right? If you do 2, 2, 2, 2. This way, I believe that we will be able to access. For example, if I do X here, right? X train shape 0, 2, 2. What if I do 1? No, it's 2. But if I change this to, let's give it, let's run again. Okay? So you get a list. No, this is nice. This is a list. So you have you get a tuple with a list inside. Maybe not. Let's see. String shape. This will be, I think it's a 3 now, right? No? What is crying? M X train. Weird. Oi, I'm so used to the Mac that I just do this naturally. Okay, okay, okay. 2, 2, 2. X train. What if I do 1 is crying? Why is this crying? I don't know. Okay, we got it. We got the idea, right? We got the idea. We can. I don't want to overcomplicate things. Let's just let's just keep going. We understand that we get a tuple. We learn what's a tuple in Python. It cannot change. Okay, cool. This could refer. This is for printing. Okay. So let's fix this error. There you go. Okay, so one can also use len function as shown below. Okay, you can do give me the len of X train. What about Y train? Okay, number of training examples. Cool. You will use X index and Y index to denotate the number training example. I know that since Python is zero index, X0 and Y0 will be 1.0 and 300.0, right? And X1 and Y1 is 2.0 and 500. which are right here. First entry, second entry, xy, x0, and x1, and y0 and y1. Okay, we understand now. Now we can get. We're going to run the next code block below to get the training example. Okay, so we want to get. So you change this, the index. It can be 0 or 1 or whatever. Then you do x index underscore index will be to x train index. So it will be 0, right? Okay. It will get you the same for the y train, and then it will print those. There you go. This is nice. This is interesting. So you get x o y estimate. Okay, x hat and y hat o equals to 1.0 and 300. Okay. So it's giving you the x-axis and the y-axis from the 0 index and the 0 index. In this case will be 1 and 300. Mm-hmm. Okay. And in and equals to the y. Mm-hmm. So if I do, give me the index 1, it will be will be this one right here. Will be the 2.0 and the 500, correct? 2.0 and 500. Okay. So plotting the data. You can plot these 2 points using a scatter function in the matplot library. Okay. So this scatter function will help us to plotting the data as shown in the cell below. The function argument marker and C show the pointer as red crosses. Okay. Marker and C show the points as red crosses. The default is blue dots. Okay, you can use other functions in the matplotlib library to set the titles and labels to display. Okay, so how do you plot the data points? We're going to use the matplotlib library and use plot scatter the scatter function. We are going to pass in x train, y train, a marker x, and z for r. I don't know what's red crosses. Okay, so we're passing red crosses, and the marker is, I guess it's going to be an X on the. Then we change the title, housing prices. Let's change that. How much? How much the house? And then every the Y label will be price in dollars. Let's just do USD and size. Okay. You use scatter, you set the title, you set the Y label, you set the X label. Then you show it. Boom. There you go. X, Y. In thousands in USD, from 300,000 to $500,000. So you have everything in the middle, and the same for the x-axis. So you have the size starting from 1,000 square feet to 2,000 square feet, which are the it range from the data points that we have. Okay, so it's just creating a red cross, right? What if we do something like O, and then we do blue? What happens? It changed. It's nice, right? So you have a different. How much the house? Okay, if it's 1,000 square feet, it an estimate will be 300,000, right? $300,000. And in the other hand, you have a 2,000 square feet house. It will jump not. It won't double. If you see that, it will jump to 500,000. It's not double. So this we can see the pattern now. Okay, um, model function. You see, so we have the model function. As described in the lecture, the model function for linear regression, which is a function that maps from x to y, is represented as, okay, this is a function, FWB, weight bias, x index equals to weight x index plus bias. The formula above is how you can represent straight lines. This is how you represent a line. That's it. Different values of W and B give you different straight lines on the plot. Okay, okay. So we have set every parameter here, right? So we set a label, we set like title, every label for Y and X, and we put we are setting the dots. But now we need to pass in a function to have this linear regression representation. So let's try to get a better intuition for this through the code blocks below. Let's start with weight. Okay, so we change the weight to 100 and the bias to 100. It's going to change. So now you can come back to the cell to use the models. So we have weight of 100 and bias of 100. Now let's compute the values, okay? Now let's compute the values of f, w, b, x index for your two data points. We have to compute two. You can explicitly write this out for each data point as for x 0 index, comma, f wb equals to w times x index 0 plus b. Okay. The only thing that changed here is the index, the x0 and the xy. We are based on the weight. Okay. For large number of data points, it can get unwieldy and repetitive. So instead, you can calculate the function output in a for loop as shown in the compute model output. Okay, this is cool. Okay, yeah, because it's just changing the index. So just go through each of them. Each iteration will have a different index. So then you can get that. Okay. The argument description and the array model describes an n-dimensional array of shape M. Scalar describes an argument without dimension, just magnitude. And P0 will return a one-dimensional NumPy array with n entries. What the hell is that? Okay. The argument description and the array. This is a tuple. Oh man, I don't understand. Describe NumPy, blah 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 blah. I don't understand. I'm going to keep there. Let's just keep going. So we have a function here. We have a compute model output. Okay, it gets an x, a weight, and a bias. Compute the prediction of linear model arguments. There you go. It's an array data examples. Oh, okay. The data examples. That will be a scalar. I don't know what is a scalar. I don't know what is an end array. So we are going to learn this stuff for the next session. We're just going to go through the Jupyter notebook right now. So M is equal to X shape index 0 FWB MP0M. We're doing a for loop in range of M, which is getting X shape. Remember, it's going to give us the length of the training set, right? So it's going to be a 2, and it's going to iterate 2 times through each of them, and it's going to output this thing for XY and for X2. For each cell. Each cell is represented by this. Okay. So it will return. Now the scalar commute model, let's see. I'm just going to call it. We just define this function. It would get the x with the length of the model of the training set. I'm getting. Okay. That's good. FW. Now let's call the compute model function. The FW is equal. It is just referring the function, passing in the x train, the weight, which is 100, and this is 100 also. is going to plot our model prediction, plot X train. We are passing in the compute mod, the compute function. We are passing in just the C, which I believe is the color, right? Which is going to be blue. Then we are changing label, okay, and then we pass in with the scatter function. We are passing in the X train, the Y train with all the lengths. We are passing the marker, red, actual values. Okay, 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 okay. We are just passing in. Okay, got it. I'm kind of getting it. And then we do again. We set the titles, we set the labels, we set the Y label, we set the X label. We are using this legend new. I haven't seen, and then we show. Okay, there you go. So this is nice. So in the first one, we just define right the data ranges, and we set 2 points based on the data points that we have. But with this function, we are using the line. We are creating a line using a regression model. So is our prediction right here. This is nice because based on this we can tell, based on these factors, weight and bias, is not a result of line that fits our data. So okay, so we need to change the weight and the bias, and it needs to properly fit this line. And this way, when we have a straight line, we might be able to predict the number based on the size. So if we put this right here and right here, and we will be able to tell, okay, a 1.4 square feet house value will be around 300 and $380,000. So, but you need to first put it in the proper way. So we will change that. Try experimented with different values, WB, and what should the values be for a line that fits our data. You can use your mouse to click in the green hits below. Oh, nice. Okay. So if we do, if we, let's just we saw the answer, but come on, let's just change this to let's just change it less. Let's do 50-50. Does it change? I don't think we need to redo that. I don't know. You see, it's going down. So it makes sense that if we put 200 here, it's going to be good. What about the bias? Let's change the bias to something like crazy. No, 500. Let's try it without running the. You see? So bias, you change bias and it will just skyrocket. Let's just keep 100 here. And do 50 and 100. Let's see how it goes. Okay. Let's do 200. 200. There you go. So now you can see. You can now predict with this. Like passing is like 100, 200 and 200 and 100 on weight and bias will give you a straight line throughout. It will fit the data. Okay. So now we can do things like, okay, 1.2 might cost around $340,000. Good. So as you can see, setting W does not result. Challenge are experimented. We already experimented with it. Prediction. Now that we have the model, we can use it to make our original predictions. Let's predict the price of a house with 100 1200 square feet, since the units of x are in thousands of square feet, as it is 1.2. Okay, so okay, that's cool. Now we can change that 1.2 base. Wait, 200 bias 100 x x index will be 1.2. The cost of the square feet of the 1200 square feet will be weight times x index plus b. Because now we have the function that they can work with. Okay, there you go. That's what I predicted. Okay, perfect. Congratulations. Woo! In this lab, you can learn. We have learned linear regressions build model, which establishes a relationship between features and targets. Yeah. Okay. In the example above, the feature was house size and target was house price. For this linear regression, the model has two parameters, W and B. Those WB values are fed using training data. Once model parameters have determined the model, can be used to make prediction on novel data. You know what? Print complete. Ta-da! Excellent. We did it. We did it. So I think this is enough for a studying session. It was great. We learned a lot today. It was fun. We're going to keep working and learning about this. Let's just do a quick recap. Okay. Uh, Basically, what we did was to learn how to represent values and how to predict numbers based on values. And we learn how to plot that data and how to pass in a formula that we can use that represents a linear regression, and based on data points that we have data points and we have a function. So we feed these data points to this function, and it will give us a way of knowing a number. So it will give us a base formula that we can pass other variables. For example, the size of the house in this case, you can change that if you have two data points only. Yeah. So if you have two data points only, 1,000 square feet and 2,000 square feet, and this cost 100,000, and this another one, what was the price, like 200,000, and this one like 4,000. So we need a way of represent this in a chart, right? To passing points, but with a formula we need to create a straight line, and this straight line has to meet that data points. Also, how do we create this line? We have this formula. And the weight and the bias is what we change. So we can have weight can be 100, it can be 200, this can be 100. And the line will change depending. So we have to find these values in order to get this proper model to work. And after getting this formula, we will be able to pass in another value. Like, I don't know, how much is 1.4? So we pass in the 1.4 to our new formula that we have here, which is basically this one. Mm-hmm. W times plus B. This value here, so when you do 100 times, no, this was 200 plus time 1.4 plus the bias, it will give you something around. It will give you 200. Wow. It will give you a value around something. Yeah, all wrong. I didn't like it, but it was wrong. Okay, this is not going to make it. For started, man. Okay. Okay, I hope you enjoyed this session. It was fun. I didn't like the recap. Just do it by your own. I didn't like the recap, but that's good. Okay, I hope you learn. It's very, I'm always, okay, let's finish this. Bye.